Welcome to everybody online, and welcome to everybody here in the room as we do our seminar series. Today's topic, Toward a Circular Carbon Economy. Plants do it, why don't we? Circular economy, reverse logistics, circular supply chains are very, very hot now. Finally, it's good to see people putting focus on it. And I'm looking forward to this discussion, the unique tie to the carbon economy and plants. I think this is going to be very interesting to see how this all ties together. And Professor Matthew Realff will be leading the discussion. He's a professor in Chemical and Biomedical Engineering, and he's also a senior fellow, and is also associated with the Strategic Energy Institute. So he looks at things from a whole bunch of different angles. Please join me in welcoming Professor Realff.
So thank you, folks. What I'll try to do, and I've got a presentation that hopefully lasts about 45 to 50 minutes, is I'm going to talk about how we might circularize our carbon economy. And I'm going to start by motivating why we need to do it, which I think is fairly obvious, but I really want to give you some fairly specific metrics and where we are with regards to this particular journey. In terms of reverse logistics and the whole question of circular economies, this is a topic that has occupied me since 1995, actually. I actually have worked for a very long time period on the reverse logistics and recycling of carpet, which is a major product here in Georgia, and continue to do so today, but that will not be the topic on which I will try to engage you. So as I say, this is going to be my topic area, and I want to immediately draw attention to the fact that a lot of people have helped me in this particular endeavor, particularly in chemical engineering, Chris Jones and Ryan Lively, over in the School of Public Policy and Economics, Emanuele Massetti, in the School of Chemistry, Joseph Sadeghi, in the SEI, Rich Simmons, and in International Affairs, Adam Stolberg. So there's been a lot of input and thinking around this particular topic. So where I want to start with is obviously what we do currently. What we do currently is we actually dig hydrocarbons and reduced forms of carbon out the ground, either in the form of oil, gas, or coal. And we release those CO2 from these hydrocarbons to the atmosphere. And as part of doing this, obviously what we do is we generate an enormous flow of wealth to various different societies, and we ourselves benefit enormously from this conversion process in terms of the energy intensity of the lives we lead, okay? So what we see about this system is it's a very unevenly distributed set of global resources. It's a multi-trillion-dollar industry, dominated actually by a relatively small number of players as an industry. And one of the questions, or really one of the questions that I have with regards to this in terms of circularizing the carbon economy, is how we can think about not only addressing the CO2 accumulation problem, but also how this might lead to a different economic arrangement in terms of the way we use resources around the globe. So could this actually drive a more equitable distribution that is not dominated, say, by a few players? Now, this curve is very famous. It starts in about 1950 when we first started measuring CO2 on Mauna Loa in Hawaii. And it goes up inexorably from 1950s to now. And you'll see that there is a small red wiggle around this curve. And that small red wiggle is actually the northern forests breathing in carbon and breathing out carbon on an annual basis. Now, why I point that out is it shows you that you think about the growth of leaves in the northern hemisphere. That seems like an awful lot of carbon being pulled in and pulled out. Well, it is, but look at what difference it makes to the overall shape of this curve. Hardly anything at all, right? So the whole idea of the cycle of carbon coming in and out of leaves is a perturbation to this curve, okay? So I'm not going to talk any further about coal today. I'm going to focus on hydrocarbons. And I'm going to point out that on February last year, we had about 419 parts per million CO2 in the atmosphere. And at this point, we are now at 421. And this increase of about 2 parts per million per year is fairly consistent at this point in our history, okay? So we're able to noticeably see the difference year to year in the accumulation of carbon dioxide in our atmosphere. Now, why I say hydrocarbons and why I want to continue to think about hydrocarbons is because I don't think those are going to go away. So much as we talk about the energy transition, most sort of organizations like, for example, the International Energy Agency, they don't project that actually hydrocarbons are going away in quite the way that we may think through popular press that we read. So if you look at this curve here, this is the absolute amount of energy that we're using. And this is the expected way that that energy will go over the next several years. And what you'll see is that the share of fossil fuels will indeed decline from its current level. It will decline significantly from 80% to 60%. But in terms of the absolute decline in the amount of fossil carbons that are used, that absolute amount is declining only by a relatively small percentage, only about 4%. So even though it's going to be a diminishing factor in our energy mix, it's going to still continue to be a very dominant player in terms of the amount of CO2 we emit in an absolute sense to the atmosphere. Okay, so hydrocarbons are something that we're still going to have to address in some way. Okay? Now, one way to look at this is to think about our remaining carbon budget. And this is a table that I find to be quite helpful in doing this. And this is taken from the most recent IPCC report on this subject area. And essentially what it does is it says this is the kind of the level of warming that we're thinking about. So 1.5 degrees C to 2 degrees C. And it basically says, what do we have left to do? Because we've already warmed by basically 1.1 degrees to this point. If we take that remaining temperature limit and convert it into the amount of carbon dioxide we would emit, and then we attach some sort of probability to meeting this target, and this probability is essentially computed by thinking about the different models that project the way that the global climate is going to evolve over the next 100 years or so. Basically, if you pick a 50% probability, i.e. flip an unbiased coin, and you say we want to keep warming to about 1.7 degrees C, and here I'm abandoning 1.5 right off the bat because I don't think that's going to happen, you'll see that we're going to have a total remaining emissions of about 850 gigatons of CO2 per year. Okay, that's our remaining budget to keep the temperature increase below 1.7 degrees C with 50% probability. Okay, so that's not a particularly conservative, goal, right? If we look at the amount we emit today, we emit roughly 40 gigatons of carbon dioxide per year. So what that tells you is that within approximately 20 years, 21 years, right, we are going to be reaching this limit. So, I could ask you for a show of hands, how many people feel like we're going to avoid emitting 850 gigatons of carbon dioxide over the next 20 years or so? And the answer is I find this extreme to be highly improbable, which makes me believe that in fact we will have to do something about the carbon dioxide that we accumulate in the atmosphere. So what that says is that negative emissions, i.e. pulling CO2 back out of the atmosphere, is going to be a required technology within the next 20 to 30 years in order to sort of meet these types of targets. Okay? So, if we look at this in another way, if we emit at our current rate, i.e. 40 gigatons per year for the next 20 years, and then we cut our rate by 75% over the next 30 years, which is a pretty tall order, but you imagine we might be able to do that. There are some pathways that models have suggested that we could do that sort of cutting. And then we held the rate steady for the rest of the century because that sort of leaves this hard to decarbonize part of our economy left. What happens to our CO2 in the atmosphere as we go from roughly 420 parts per million to 520 parts per million? In other words, we add roughly another 100 parts per million CO2 to the atmosphere. Okay? So how are we going to walk this footprint backwards? And how far do we have to walk this footprint backwards? Because that's really the concern that we have. So if we were actually to pull all 100 ppm back out and get back to where we are today, that would require 780 gigatons of carbon to be removed, which if you do the math from 2022 is roughly 10 gigatons per year, okay? If we only want to reach the point where we actually are at 1.7, that corresponds to pulling about 390 gigatons of carbon out of the atmosphere, which is roughly 4 gigatons per year. And that is still 4 gigatons per year, right? That's a lot of carbon dioxide. So we will need negative emissions, and I think significant negative emissions, i.e. 1 to 10 gigatons per year within the next 20 to 50 years, okay? So how are we going to achieve massive negative emissions? That's really the question that we have to ask, okay? Because that's going to be a new industry that will be completely different from the industries we've built before, except in the case of one particular industry, which is, of course, the forestry industry, right? The forestry industry is an industry which today pulls carbon out of the atmosphere by growing trees, right? As long as they don't cut them down and use them for anything, right? So that's the question we have to ask is, how can we combine things like forestry and other negative emission technologies to achieve this kind of goal of negative emissions in this range, okay? Now I'm going to talk about some negative emission technologies, and I'm going to go through each one of these negative emission technologies, but then for most of my talk I'm actually going to focus on this technology, which is direct air capture, which is the technology that I feel can scale to the necessary levels to be able to meet this kind of 1 to 10 gigaton a year target. But I am going to talk through each one of them. So the first one is, for example, coastal blue carbon. So a lot of people are very interested in this idea of promoting the growth of plants, things like seagrass, seaweed, etc., along the littoral shores of various different continents, okay? This is a possibility, but right now we don't really know how this works. It's relatively low cost if we can make it happen, but if you look at the total amount that could address, it's not a very sizable component of a 1 to 10 gigaton industry. Another one is biomass, and I think this one has some significant promise, and there are really a variety of different ways in which CO2 can be sequestered by natural processes. One is to just grow trees and leave them standing, okay? One is to sequester more CO2 in the soil by changing the distribution of plants we grow, which will essentially enable us to have a higher sequestration in the roots. And then the technological solution is actually called BECCS, or Bioenergy with Carbon Capture and Storage, which has also been retitled BICAS, which is basically bioenergy with carbon removal and storage. Okay, those technologies, we would take the biomass, whether that be residue biomass or freshly grown biomass, and we would actually burn that in power plants, generate energy, electricity from that, and then we would take the CO2 that we actually would traditionally emit from the stack and actually capture that CO2 and sequester it in geological formations, okay? So that would be the way in which we would address this particular concern. And of course, what it's basically doing is using trees to suck CO2 out of the air and then using power plants to make the CO2 or make the carbon into a more concentrated CO2 form, then put it in the ground, okay? And this has good costs, relatively speaking, less than $100 a ton, and it's moderately scalable. That is, we have land available that we could use to do this kind of approach. But remember, that land is always under competition for other things. So if we want to do agriculture or other types of activities, we have to recognize that will compete with this particular use if we start to take some of our agricultural lands and do it this way. But in the US, we have a lot of forestry land. This might be an option that we can pursue. The third option is really to do either some direct air capture or to do some accelerated chemical weathering of rocks. And these are technological interventions that directly operate on the CO2 and try to effectively remove them. Now, in the case of accelerated weathering of rocks, you basically grind rocks up and you expose them to the atmosphere, and those rocks are capable of reacting with the CO2, and so they directly sequester the CO2 into a rock mineral form, okay? That would be the idea of this, okay? Here, there are many basic research questions around carbon mineralization that have not yet been solved, so that's a nascent technology, but not one that's really yet deployable. The other one is direct air capture, and direct air capture, you essentially use a machine to try to remove the CO2 from the air, and then you take that CO2 and sequester it into these geological formations. And I'm showing two different types of geological formations here because one of them, effectively, you inject the CO2 at a relatively high depth, and it goes into a saline aquifer, and it sits there as CO2. Okay, so it stays as CO2. The alternative is to actually use a basalt rock or a mafic or ultramafic rock, and that mafic or ultramafic rock will actually react with the CO2 and sequester it in the form of a mineral. So basically it's instead of digging the rocks out of the ground or having the rocks exposed at the surface, what it does is he says bring the CO2 in concentrated form down to those same rocks and actually do the reaction in situ. Okay, so that's the alternative. That's the idea of this. And this is being practiced today at moderate scale, thousands of tons a year, by one of the direct air capture companies, and it's being practiced in Iceland, right? Now, why would you practice this in Iceland? Because Iceland is basically a large volcanic rock, right? So if you fracture the rock of Iceland and you pump CO2 down, you're effectively enabling yourself to access a large basaltic deposit, okay? And there are basaltic deposits that are accessible various places around the world, including the United States. Okay? Now I'm going to talk a little bit about why direct air capture might make sense, okay? So I'm going to take a couple of slides to explain why it can work, and then I'm going to show you a system that sort of embodies those types of concepts to be able to do this, okay? So here, what we have is we have this feed, and this has my 400 parts per million of CO2 in it. And what I'm going to do is I'm going to recover a certain amount of that CO2, in this case 90% of it. So for every kilogram of CO2 that flows in at the front, 0.1 kilograms will come out at the back, and I'll capture 0.9 kilograms. And I'm going to capture it with a certain purity, 95% purity, which is it's a reasonable purity at which to capture CO2. Okay? If I do this, I can actually plot how the amount of energy it takes to do that separation, in theory, varies with the concentration of the gas, of CO2 in the feed gas, okay? And what you can see is that the difference between capturing flue gas, which is at 10% CO2, that's the stuff that's in the exit of the BECCS facility, the biomass facility, versus capturing it from air, which is about 400 parts per million, the theoretical energy only doubles. Okay, so the theoretical energy doubles, but the concentration is reduced by a factor of 250. Okay, so this turns out to be just a result of the way that the energy scales with the feed concentration, which is logarithmic. Okay, so it's a logarithmic scaling of the energy required based on the feed concentration. But it is a very different looking separation from some of the stuff we do today because it's very dilute. We have to separate a very dilute component out of a very large stream. And that requires we think about our separation process here differently from the way we would do for most types of separation processes. So, is air capture possible? And this hopefully will suggest that it is. So we started with this idea of a dilute input stream with a separation process that was going to make my CO2 and reject my air. Okay? Now, with dilute separations, the real question is where do you put the work in? In other words, where do you apply the energy necessary to do the separation? So if you think about another dilute separation, one dilute separation is, for example, mining. We do a lot of mining to recover gold from ores, and the gold appears very, very small concentration in the ore, right? But we do all the work to recover that gold up front. We do all the work to dig the rocks out the ground, crush them, and then react the gold with a component to be able to separate it from the rock, okay? So most of the work is applied up front. In the case of direct air capture, what we're going to do is we're going to flip this around, and we're actually going to have something that's spontaneous on the front, i.e. something that actually releases energy on the front to remove the CO2 from the air, and then we're going to apply the energy on the back end to release the CO2 from the material into which we captured it. Okay? So what that does is it fundamentally changes the amount of if you like, parasitic load that the system places on processing the feed. If we can put a small amount of energy into the feed and a large amount of energy here, then maybe we can achieve dilute separation with close to the energy efficiency of the 20 kilojoules per mole, where we started, right? So that's the idea. The idea here is spontaneous upfront process, non-spontaneous energy-consuming process on the back end. Okay, so what are the key components to make this happen? Well, essentially, what we need some way to contact the air with the adsorbent material in such a way that it does so with low pressure drop and with moderate cost. And so here I'm showing an example of this, which is a ceramic monolith. This ceramic monolith, you may not be able to see this, has lots and lots of small channels in it, and the air will flow through these small channels, and it will flow through with relatively low pressure drop, right? Does anybody know where these ceramic monoliths are used today? Catalytic converters, okay? So your car, if you have unless you have an electric car, in which case you don't have one of these, right? Your combustion engine uses a monolith like this to reduce the pollutants from the tailpipe. So you coat this today with platinum or a precious metal, and that platinum or precious metal reduces the pollution and actually makes the car have less nitrous oxide and other emissions, okay? So that's where they come from today. Now, an alternative is something called a hollow fiber, and this, you won't be able to see the size here, but this is essentially the width of a human hair. It's about 1,000 microns, and what it does is it has a porous polymer that is here, a plastic, and inside of that we can embed our adsorbent material, okay? So this is another alternative. So this is easily coated with adsorbent materials. It has rapid heating and cooling by flowing a fluid down the bore of this particular fiber, and then the sorbent is in this annulus, okay? So both of these are today commercially available. They're both relatively low cost, and key, because we don't want to put in a lot of energy into moving the air, the energy moving the air is low because it has low pressure drop. So this is the idea, right? The idea is we put very little energy into the front end of the process, i.e. moving the air through the contactor, and we put all the energy into removing the CO2 from either the monolith or from the fiber on the back end of this process. That's the idea, okay? So how does this work? Well, here's an example. Here's a monolith coated with the sorbent on the inside of the channel. I'm showing you the adsorption step here where the air is coming in and the concentration of CO2 is building up inside the contactor, okay? Then when we go to desorption, we blow steam into here, and what the steam does is it heats the monolith up. That causes the CO2 to desorb, and the steam pushes the CO2 out of the monolith at the back end. So what you do is you end up using steam to both desorb and move the CO2 out of the monolith, okay? That's the idea. So this has relatively low energy consumption, just the air moving through the contactor, and here's where you're using your energy because you're blowing steam, and steam is, you have to make the steam, so you have to boil the water. This is where you're putting the energy into the process, okay? Now, a typical analysis of this means that we would use, in terms of energy consumption, about 250 kilowatt hours of electricity to move the air, and about 1,750 kilowatt hours per ton of CO2 to use the steam. Okay? The capital cost of something like this will be about $730 per ton capacity of CO2 per year, and the cost would be roughly $150 per ton of CO2 for this type of system. Okay? So that's sort of the cost target that we're looking at is $150 a ton. We'd actually like to be much lower than that, but today you might think that we could achieve something like $150 to $300 a ton of CO2. This is probably a low-end estimate relative to the current maturity of the technology, okay? So here's a monolith contactor, and here's a direct air capture machine, okay? So this is the technology that is being essentially demonstrated by Global Thermostat, which is one of the startup companies in this space. What you'll see here is you'll see that there is a lower part and an upper part of this structure. The upper part of this structure is large, cylindrical devices. What do you think these are? Fans, right? So you put a fan on the top of the device. You pull the air in through the sides. The monolith bricks are actually hidden behind these louvers here. So the air is going through the monolith bricks and up out the top of the device. The monolith bricks are in contactors that can move around this device. And once in a while, they arrive at this station here. And this station here has a bunch of pipes. this is where you use the steam. So you're using a moving device that moves the bricks through the air, and every so once in a while, they go to the desorption device, and the desorption device pulls the CO2 out. And the ratio of the number of contactors in desorption to adsorption is based on the ratio of the time it takes to get the CO2 into the monolith and the amount of time it takes to desorb the CO2 from the monolith. Okay? It's a nice ISYE problem, actually. Okay? So this is the type of device that's built, and this will capture a few thousand tons a year of CO2. Okay? The individual stood here. This is Eric Ping. Eric Ping is the current technology officer of Global Thermostat. He is a former PhD student from Georgia Tech, worked in Professor Chris Jones's group. These three individuals are from a company that are reviewing this technology to see whether or not they wanted to buy it. Okay? So this today sits in Brighton, Colorado. Okay? That's where it is. And in fact, they are in the process of upgrading this unit and demonstrating that indeed they can capture multiple thousands of tons of carbon dioxide per year. Okay? So this shows you that this is where the status of these kinds of systems are today. There are other technology companies that are reaching similar scales, and I mentioned the one in Iceland that is already operating. Okay. So how does this relate to circular carbon economy? Well, what I've tried to demonstrate is that CO2 capture is a feasible technology. Okay, that's what I'm really trying to say here. And that what we're going to be doing is using renewable energy to both power our current energy uses, but also we can use renewable energy to capture CO2, and we can use that renewable energy to convert CO2 to liquid fuels. So the idea here is that we take our renewable energy and use that as a way to capture both CO2 and turn that CO2 into liquid fuels, thereby replacing the hydrocarbons that we're digging out the ground, right? So this circularizes the carbon economy and enables us to continue to use liquid fuels as a way of having our energy systems, okay? Now, why is this a good idea? Well, liquid hydrocarbons, it turns out, are really a very good way of carrying energy around, right? This is really the point of why we want to continue to use them. They've got very high energy density, about 45 megajoules per kilogram, whereas if you look at your current generation of lithium-ion batteries, those are about 0.54 megajoules per kilogram, right? This is why your Tesla weighs multiple, not your Teslas, but whoever owns a Tesla, right? This is why they weigh thousands of kilograms, because they've got thousands of kilograms of battery in their floorboard, right? Whereas what you have in your conventional powered plant is you have a polypropylene tank which you fill up with gasoline, and how big is that? It's about 15 to 20 gallons typically, right? So the energy density is the reason that they're good in this sense. They're also easy to pump, and they're very cheap to store, right? We have an enormous infrastructure devoted to storing liquid hydrocarbons already today, right? And it's very cheap. And we have a lot of infrastructure to use it, right? If we didn't have to replace people's cars, that might actually be quite a useful little trick to play, right? Not that the car companies think that that's going to actually happen. But maybe it's not really cars, it's maybe the heavy-duty trucks, it's maybe the aircraft, it's maybe some of those much harder to decarbonize components of our energy system in which this will fit very naturally, okay? So, what are our current investments in this field? Well, we did a study a few years ago, and what we showed is that the hydrocarbon transportation sector is about an $8.4 trillion dollar investment, okay? And most of this investment is spread between government and private assets, and it's about 500 and 140 billion in each. And this doesn't include any jobs or ancillary items or anything else in the infrastructure. This is just the direct investment, okay? And that is distributed between a variety of different places, okay? So if we look at the private sector assets at 5.5 trillion, this is basically embodied in things like trucks, buses, and truck trailers, non-vehicle transportation, machinery and equipment, and that's roughly, about half is in that category. Then there's other commercials, power, and then there's petroleum and natural gas. So this petroleum and natural gas is about a third of our investment, and this is the sort of thing that we could get to reuse if we could figure out how to couple these things together, along with being able to take some of this investment and continue to reuse that, because essentially it'll still be there 20 years from now, right? That's kind of the point, right? We will still have a significant fraction of this kind of infrastructure 20 years from now if we could develop this kind of technology today. Now, if we were able to use this type of system, right, what we can do is we can go ahead and start thinking about converting the liquid fuels and using this as an energy storage system, right? So basically, we have a large number of tanks located in various places across the United States. We have a huge pipeline infrastructure, and we have a very significant distribution infrastructure for gasoline. Okay, and for diesels and other types of liquid hydrocarbon fuels. So all of this infrastructure could essentially be used as part of an energy storage infrastructure. And oh, by the way, this is extremely stable and long-lived. So this enables us to move energy not only in space, but in time, which is very difficult for batteries to do. So batteries find it very difficult to move energy across long time periods because they like to charge and discharge on a regular basis. They don't like to just sit there and have the energy stay there and then get reused at a later part of the year, right? Now, the reason I bring this up is because if you think about somewhere like even Arizona, the variation of sunlight between winter and summer is 40%. So you have to think about what the infrastructure implications are of being able to meet needs in the winter versus needs in the summer, and whether in fact you should be time shifting energy from the summer to the winter by using things like efficient long-term storage devices. Okay, that's the implication of this. Okay, so let's look at that storage in a little bit more detail. So gasoline storage, as I say, is about 8 to 9 megawatt hours per meter cubed. And if we look at large-scale storage of gasoline, a large scale is about 1 million gallons, okay, with a capital return factor, CRF factor of 0.13. That means it costs us about 1/6 of a cent per year per kilowatt hour of capacity. And that capacity is about 33,000 megawatt hours. The largest storage we have for electricity today is something called pumped hydro, where basically we pump water uphill. And if we look at the capital cost of that, it's about $165 per kilowatt hour, right? And if you again use the same capital recovery factor, it's about $21 per year per kilowatt hour of capacity. All right? That's a mere 4 orders of magnitude more expensive to store electricity than it is to store gasoline in this regard. Okay? Now, if I look at small scale, picture changes a little bit, right? My gasoline station, right, my petrol station, it's 36 gallons with about a 30-year life. That's about 10 cents a year per kilowatt hour of capacity, and it's about 1.2 thousand megawatt hours. A lithium-ion battery is about $200 per kilowatt hour of capacity, which again translates to about $26 per year per kilowatt hour of capacity. So again, it's not quite as significant at this scale, but it's still pretty significant in terms of the difference. Now, we have a 36 billion gallon tank farm in Cushing, Oklahoma already. This already exists, which is 1.2 billion megawatt hours of storage capacity, okay? And we have the US Strategic Petroleum Reserve, which is an order of magnitude larger even than this. The largest example today of a pumped hydro is about 38,000 megawatt hours, all right? So 1.2 billion versus 38,000. The entire installed grid capacity in 2018 of battery storage was 1.236 thousand megawatt hours, okay? And I talked to someone at Georgia Power, and he says, we've got 3 minutes of storage for electricity in the US. So, you know, if the grid goes down, you know, our storage capacity is about 3 minutes, right? So I don't know, I'm not very comfortable with the idea of having an energy system that sits there and 3 minutes later could be, we have no energy, right? So this is what this kind of thing does. It buffers you with regards to failures. It enables you to have much larger scale storage than you can really achieve with these types of systems today, okay? That's kind of the point here. So how do we do it? All right, this will be my last few slides. The way we do it is well, we've talked about getting carbon dioxide. We can get water. Water's available basically globally, but has regional scarcity, okay? But we can get water. We can even take water and get it from the ocean. We can do something called reverse osmosis, recover it from the ocean. That takes a bit more energy, but it's not significant in the overall scheme of things. We can take renewable energy, and there's going to need a lot of renewable energy, don't get me wrong. And we can then use chemical technologies, and we can reduce the water and the carbon dioxide, and then we can take those reduction, that hydrogen and that carbon monoxide, and we can use that to produce the kinds of fuels that we use today, such as alkanes and methanol, okay? Or we can take that H2 and CO, which is just pulling an oxygen off this carbon dioxide, and actually use it in biochemical processes to produce alcohols and fatty acids, okay? And this is what LanzaJet is doing today, okay? So LanzaJet takes these types of compounds and actually ferments them to alcohols, ethanol in their case, and actually then makes jet fuels from those. That's what LanzaJet does. LanzaJet actually has a facility out in Dublin, Georgia, as one of their facilities. Okay. Now, one more thing I'll point out here about why this sort of new system might be useful is if you look at the path of Tropical Storm Laura, which is just one that I happened to pick from 2021, 10% of all oil production is located along essentially the path of this type of hurricane. 20% of US refinery capacity was located along this specific pathway. And 29% of the US capacity to produce ethylene, which is a very significant commodity chemical and at the base of a lot of our chemicals, about 29% again was shut down by Tropical Storm Laura. And 89% of US capacity to export shale gas is located in this region, right? So what this says is that concentration of infrastructure is quite vulnerable to disruption, okay, from various different events. Maybe we could actually have a more distributed fuel production and have a much more resilient supply chain. So that's another advantage that this kind of system could afford you. So what we have today is we have this globally interconnected system at very large scale that eventually delivers fuel to your vehicle. What we could do is we could replace that with a regional system that had a much more distributed structure, where in fact you have direct air capture, you have renewable energy, you have chemical conversion technology that produces fuel at the scale, if you like, of a gasoline station, not at the scale of a refinery. And then this kind of regional or local modular scale could be reproduced around the globe, thereby distributing the economic benefits of using hydrocarbons from the current very concentrated sources to a much more distributed system. And really the challenge is how do we combine these systems together in an energy transition, right? How do we go from our large-scale infrastructures today to something that might look more like this in the future? How do we blend these together? What's the right blend? How should we look at this? Okay, so in summary, what I'd like to propose is that we have today this linear production, refining, and use strategy, which we could transform into a circular strategy to essentially capture, convert, and use carbon effectively with carbon dioxide in this frame and hydrocarbons in this frame. It would enable us to reduce the flow of fossil carbon to the atmosphere because effectively we'd be cutting off requiring new hydrocarbons to be dug out the ground and just be essentially making the carbon dioxide back into hydrocarbons. We can use this captured CO2 as a resource for economic activity, and I've argued that this industry is really huge, right? Trillions of dollars are already in the hydrocarbon industry. It enables us to have much more localized energy and carbon-based materials and chemicals production to enhance the resiliency of supply chains. It minimizes the disruption of moving to renewable energy by reusing this infrastructure, and it improves the efficiency of renewable energy production, use, and storage. Okay? All right, so I'll stop there and be happy to take questions.
Questions?
Yeah.
Sorry, I just remembered that. I was wondering, So you mentioned a lot of these solutions, and I was just wondering what parties might be interested in actually implement or responsible for implementing these solutions that you've mentioned.
So that's a good question. So the people that are implementing it right now are entrepreneurs, right? So there's a lot of entrepreneurial activity in the carbon capture type of systems. There are also companies that are doing renewable fuels. For example, Sunfire Fuels in Germany is already starting to think about combining CO2 capture with water reduction, water electrolysis to make hydrogen. So there are startup companies that are doing this type of activity. There's a lot of interest from other types of companies in carbon capture, okay? One of the ones that is there is someone called Carbon Engineering, is a company that started in this space, and they were acquired by Occidental Petroleum, okay? So why did Occidental buy them? Because they see CO2 and CO2 management as a pretty significant business opportunity for them. If anybody pays attention to what ExxonMobil is saying, you should read some of their recent announcements, because they're also thinking that carbon management is going to be a business opportunity for them. And so their last purchase of offshore space in the Gulf of Mexico was not to buy it for oil, but to buy it to sequester CO2. Okay, so there's a significant interest from the major oil companies, the oil majors as I call them, the Seven Sisters, that are actually interested in this technology. But a lot of this right now is going on in the startup space. In fact, you can't throw a stone and not hit a CO2 startup right now in terms of capture. There's probably 20 or 30 of them globally.
And what would drive the economic interest in CO2?
Okay, so right now, I tell you what's driving it. It's something that's in the IRA, or Inflation Reduction Act, which is $180 a ton credit for CO2. So right today, you can get paid $180 a ton to sequester a ton of CO2. Mm-hmm. Okay, so that's what's driving the interest.
And so that's what drives your, like the $150 estimate is a good because you make $30 profit on that.
Yeah, exactly. Okay.
Yeah.
So the answer is if I today could capture CO2 at $150 a ton, I could be making a lot of money. Unfortunately, I can't do it, but that's the point. If I could, yeah, I would, right? Because if I could do a gigaton, right, that's $1 billion, mm-hmm, I'd be making $30 billion a year, mm-hmm, right?
Thank you.
I'd settle for like a lot less than that.
Has anyone looked at the energy consumption associated with creating the monoliths and the hollow fibers? Are they energy intense?
So people have done an analysis of the systems that essentially are used by the company in Iceland, and it turns out it's about 11% of the overall carbon footprint. It's a very low fraction. Most of the carbon footprint is in the energy that is being used, okay? That's today because the energy that's being used today is not renewable energy. This is the reason. If you're going to do CO2 and you're going to do capture and you're going to do it effectively, you have to be using low carbon energy. Otherwise, the energy you consume to capture the CO2 is then you've got to capture more CO2, and that really doesn't look good, okay? So if you look at some of the analyses today, it's probably only about a third to a half of the CO2 that's actually captured is actually coming from the atmosphere. The other third to a half is basically what you have to inherit from the energy that you use to make this to do the capturing, right? So you really need renewable energy to drive down your carbon footprint of capture. Now, what's the other advantage that Iceland has in that regard? Where does most of their energy come from? Geothermal. It's geothermal energy because it's basically a volcano, right? Not quite, but it is. I mean, there are volcanoes on Iceland, right? So a lot of their energy comes from geothermal sources. So you do have a renewable source of energy in that particular location, right? Now, I'm not suggesting that we take all of our carbon capture and convert Iceland to a carbon capture sort of location only. There are obviously, we could do this anywhere as long as we can find the renewable energy sources. Yeah. Wait a minute.
Thank you.
He's running.
Could you speak to any more financial tools that would drive implementation other than the U.S. with, in the event that there's a new administration and such? And could you speak to like carbon credits and all these different voluntary mechanisms, because they don't really have a legal regime that enforces them?
Right.
So I was just curious, is there anyone else? I don't know if Germany is necessarily the best.
So the answer is there's a few answers to that, and I'll give you a couple of them. One is, obviously there is a voluntary carbon market, okay? And so there are companies that are interested in this because they've made commitments to have zero carbon footprint by some date, 2030, 2035, right? Those companies have realized, they've looked at their operations, and they've realized, yeah, we can use renewable energy, and we can get down to 10%, 15% of our current carbon footprint. We have no way of getting rid of that last 10 or 15%. So this CO2 capture is being viewed as the last mile, right? It's viewed as, if we're going to be able to get to zero, we're not going to get there by getting rid of all of our carbon footprint. We're going to get rid of most of it, and then we're going to use direct air capture to fill in the last piece, okay? So some of the companies, for example, that are buying the carbon that is buying the carbon, they're not buying it, they're buying the fact that people are putting it under the ground, right? They're doing that, so Microsoft, for example, is one of the people paying for the sequestration in Iceland, okay? And they're actually paying $600 a ton. Okay, so there are some companies that really are willing to pay that kind of level of price to do this. Now, the other thing is that CO2 is actually used for things, right? It's actually used as a commodity. Soft drinks, right? The CO2 is the fizzy stuff in soft drinks. So there are places in the world that don't have good access to CO2, okay? Island nations, right? CO2 is produced at large scale in things like fertilizer plants. Those island nations don't have fertilizer plants. They refrigerate CO2 and they take it by ship to those locations. If you look at the actual price of CO2 in those locations, it could be $600 to $1,000 a ton. Okay? Now, do I think that that's going to solve the global climate problem? No. Drinking fizzy drinks is actually contributing to the global climate problem, right? So it doesn't do anything for the global climate, but if you were looking as an entrepreneur to find places where you could build CO2 capture plants and use CO2 today, those would be the locations you might choose, right?
There was a question online, how do we go from kilotons to gigatons in CO2 captured per year?
Right, so the answer is we have to have a modular technology. Okay, so I sort of pointed this out. The way we have to do this is we're going to scale this up by building a new industry to make these devices. The calculation that we've done suggests, actually this is Peter Eisenberger at Global Thermostat did this calculation, suggests that if you actually took the global car industry and took that today and used it to make direct air capture units instead of making cars, which, by the way, they won't be making those kind of cars because they won't be needed because we'll be making all these new electric cars, right? If you took that industry and repurposed it to make direct air capture units, the number of units that they make per year is an order of magnitude larger than the number of the units that I showed you that we would have here, right? So basically, those direct air capture units that I showed, the global thermostat ones, it's an order of magnitude smaller than the number of cars we make per year to capture gigatons of carbon dioxide. Okay? So the answer is we can scale this industry by repurposing parts of our existing industries that already do this sort of thing. And as long as we have it as a modular manufacturing kind of system, we can build this quite quickly, actually. So that's how we would do it. We would essentially manufacture these units and put them out in places where, in fact, we want to capture the CO2, which is what, in fact, Carbon Engineering is doing in Texas. They bought 175,000 acres in Texas, and they intend to capture millions, actually tens of millions of tons of CO2 on that ground in the next 10 years. So that's the way they think of getting to scale. Now, they're also thinking modularly, but they're thinking their modules are a lot bigger than the ones I showed you here, right? Yeah.
So one question I had was, how does this apply to developing countries that are currently utilizing these hydrocarbons to advance their economy?
Okay, so I have two different answers for that one. My first answer is they could obviously switch to this type of technology, right? They could now decouple themselves from that, those sources of hydrocarbons by capturing sunlight and using water locally to make these kinds of fuels, okay? Now that might be a good solution for them because they've got a lot of sunlight and a lot of land typically, right? Because a lot of these countries are actually located in just where you want them to be, around the equatorial region from a sunlight perspective. However, I have a different answer, which is we do the capture and we allow them to continue to use the hydrocarbons as a good source, low-cost source of energy that is compatible with their existing infrastructure that they need to grow significantly anyway, right? So I see this as a play for the US to address its historic, and the UK, well, you can tell from my accent, we've emitted a lot of CO2 historically into the atmosphere. If we took responsibility for that and actually started to pull that CO2 back out of the atmosphere, that would leave the space for those countries to in fact emit a similar amount of CO2 and reach the same levels of development, right? And I think there's an equity issue in there, really, that we can't just say, oh yeah, we put it in there, we're not responsible for it anymore, right? No, we put it in there, we're kind of responsible for it. So we could use this technology to address our historical emissions and enable other countries to develop along the same pathways that we did, if that turns out to be the choice they want to make. That's the problem, right? What we're saying today is you can't make that choice because we don't want you to emit that CO2, right? That's kind of problematic in my view.
Since the carbon capture, it needs to be compatible with the whole infrastructure of like petroleum. How would this coexist with the new EV stuff?
Well, so I don't think you're going to use this for gasoline-powered vehicles, right? I think gasoline-powered vehicles as personal transportation are probably going to go away. We seem to have made that decision, right? So what this is going to really be used for is it's really going to be used for those other components of our hydrocarbon infrastructure, such as trucks, planes, boats, etc., which are very difficult to trains. They're difficult to decarbonize, okay, because their energy intensity is much higher than that of a personal vehicle, okay? Trying to put a battery on an aircraft is a fanciful idea right now. Now, maybe there'll be some breakthrough in technology. I can't say there won't be, right? But basically today, that wouldn't be a feasible way of flying an aircraft. So I think there are going to be those sectors of the economy that are going to continue to need to use hydrocarbons. A lot of what you see around you is made of plastic, right? Maybe we're going to use these type of hydrocarbons to continue to maintain a chemical industry that's based around the types of polymers we make today, the plastics we make today, right? So that's another avenue for the use of these sorts of things. So I see this as being compatible with a smaller but still significant hydrocarbon component of our economy, and that renewable energy will shift in and start taking over. But as we make that transition, I think we're going to encounter some bottlenecks that we're not entirely anticipating, and having this as an alternative might really help us. And then the other one is long-term storage. You know, maybe we will develop batteries that have sufficient long-term storage costs that are sufficient, but if not, this is not such a bad idea. So my final remark will be, I've got one more set of slides after this that I chose not to show because I wanted to make sure we had time for questions and discussion. But I don't know, do you distribute the slides to folks?
Yeah, we can.
Okay, so you can distribute. There's a techno-economic analysis at the end of these set of slides where I go through and show you how much it's going to cost you to do this. So that's there, but it's a bit in the weeds for a discussion today. Okay?
If we have no other questions, please join me in thanking Professor Realff for speaking.